In this lesson, we've introduced a simple and expressive paradigm for concurrent programming, namely deterministic data flow. It has very nice properties. By design, it has no observable non-determinism, which is the same as saying it has no race conditions. It's simple. It's based on two simple ideas. First of all, single assignment variables, and specifically synchronization of single assignment variables on binding. And second, the simple idea of a thread, which is a sequence of executing instructions. With this model, we can build multi-agent programs using the techniques of functional programming, using streams, where a stream is just a list with an unbound tail, and agents, where an agent is a list function running in its own thread. So deterministic data flow is just a form of functional programming. So that's all very nice. Now let's put this in context of concurrent programming in the on the internet in society. The first point I want to make is that parallel programming has finally arrived and become mainstream. By parallel programming, I mean the use of multiple computing elements to increase performance by dividing the work between the computing elements so that the overall time is reduced. As an old timer, I remember in the 80s and 90s, people were building parallel computers, but it was kind of a joke because you would take the fastest sequential processor, then you would put it as the processing element in a parallel computer, and then you would have a great parallel computer, but the time it took you to put this in the parallel computer, a new and even faster sequential processor would appear, so your effort was kind of in vain. So parallel programming was always the technology of the future, never the technology of today. Well, those days have finally ended. Since the early 2000s, this is still a kind of surprise to an old-timer like me, has finally ended. And there's two examples of that. One is multi-core and the other one is distributed computing. So multi-core, multiple processing cores on a single chip, dual core, quad core, very used today, a dozen tomorrow, 100 in a decade, and the few applications that don't do it will soon do it. So multi-core gives us parallelism because chip densities are still increasing according to Moore's law, but the clock speeds are not increasing. So this gives naturally multi-core. The second point is distributed computing. So the internet is now very reliable, high bandwidth, low latency, much more than it was in the 80s and 90s. So it's a good base to build distributed applications. We also have cloud computing, which gives a huge number of systems with a high performance network in a single installation that we can use. So we therefore have data intensive distributed applications or collaborative applications with tens of nodes, for example, running today, NoSQL, MapReduce, and so on. Tomorrow they will be running on hundreds, then thousands, and so on, and more applications will take advantage. So for both of these reasons, they are both very parallel. Therefore, they require concurrent programming ideas to implement. So something has to change with how concurrent programming is done. So we cannot go back to sequential programming being the default. It's a bottleneck. The systems are naturally concurrent. Libraries can only hide so much. The interface of the library gets very complex, and you cannot hide really the distribution structure. For example, data is in different places and cannot be moved easily, cannot be hidden really. So, conclusion, concurrency will have to get a lot easier. Well, how do we do that? Well, one candidate is deterministic data flow because it's simply functional programming. And it can be extended to handle a number of the important cases. It can handle network transparency, where you have a distributed implementation of a deterministic data flow language. It can handle modular fault tolerance. It can handle large-scale distribution. So it could be the default concurrent model because it's so easy and nice. But then we have a question. It is deterministic, this model. And determinism in a concurrent system is a limitation. any program that needs non-determinism can simply not be written in the deterministic data flow model. And here's a simple example to show you how strong the need for non-determinism is. Even a simple client server needs non-determinism. So here's a figure showing a client server. So I have one server listening to two clients. So what happens? The server accepts requests from either client. At any instant in time, either of the clients can send a request, which means the server must accept a request non-deterministically. It's not the program that decides, it's which message arrives first that decides which client should be handled. So this is the system deciding and not the program. This is non-determinism, okay? So we can't do it in the deterministic data flow model. But what do we do? Determinism has big advantages too. It allows programs with, by design, no race conditions. So what's the solution? In fact, in my view, the solution is to combine both in the right way. In fact, to use deterministic data flow as a default, and in that way we reduce the need for non-determinism. In fact, in the client server, you only need non-determinism in exactly one place, at the point where the server accepts requests, right here. And because deterministic data flow is so nice, any functional program can be made concurrent without changing the results. So development remains simple. There's only, in most programs, a very small number of places where you really need non-determinism. So in my view, that's the way to go. Let me give a little bit of history now, because deterministic data flow is not a new idea. It has a long history. So for example, deterministic concurrency, the first part, the history starts in 1974, as far as I can tell. So a guy by the name of Gilles Kahn introduced this model, which is in fact very close to the model of this lesson. And 3 years later, with David McQueen, he introduced an extension which handles lazy deterministic concurrency, which in fact you can also do for the deterministic model that I introduced here. And if you look at the book, you can see the lazy version, which is also very interesting. But what happened then? This model was forgotten. Well, this was in the 70s, and message passing and monitors, so shared state, arrived at about the same time. So in 1973, Carl Hewitt, Peter Bishop, and Richard Steiger introduced the actor formalism, which is basically message passing. And in 74, Tony Hoare introduced monitors, which is basically doing shared state concurrency. And these both of these concepts then took over. Now, what do you think? Both actors and monitors can express non-determinism. So they are naturally better than deterministic concurrency, right? Deterministic concurrency can be forgotten? What do you think? The second part is the data flow aspect, which really simplifies things and causes the deterministic concurrency to be exactly like functional programming. This one also starts in 74. It's amazing how many ideas came into being first in the late 60s or the early 70s. So Jack Dennis wrote an article on the first version of a data flow procedure language. But data flow for many years was used for parallel programming, trying to build parallel architecture. Since the data naturally flows and operations are done when their data becomes available, it seemed a natural way to do parallel programming, and not so much for concurrency. It wasn't really used for concurrency. So it remained kind of a fringe subject. Parallel programming was a fringe subject until the multi-core processors in the early 2000s, the IBM Power 4, for example, in 2001. So data flow is starting to come into its own now, especially also on cloud computing. Deterministic concurrency maybe should not be forgotten anymore. Maybe it should be brought back into the center. That's what I think. In the next lesson, we will also talk about deterministic data flow. In fact, I'm going to give more information. First, some general programming techniques, what I call concurrency for dummies. Also, some more sophisticated examples using higher order programming and using nice techniques like concurrent deployment. And finally, I will really give the semantics. I will show how concurrency extends the abstract machine. And this is not just the deterministic data flow, but all forms of concurrency. And in fact, the extension is very small. So concurrency is actually a very simple thing semantically.